Welcome you all to Principles of Organic Synthesis. Presently we study the nucleophilic aromatic substitution reaction. So far in this topic we had one lecture where we studied the principles of nucleophilic aromatic substitution, where we have seen two types of reactions. First one was addition followed by elimination reaction. Next one we have seen the elimination followed by addition reaction. If you remember, in the case of addition elimination reaction, the substrate should have a electron withdrawing group. If you have a good leaving group at the ortho or para position with respect to the strong electron withdrawing group, in that case the nucleophile can undergo ipso substitution reaction via addition followed by elimination. In the latter case, we have seen the involvement of benzene intermediate if the aromatic system has halogen which is not activated. Those substrates can be reacted with a strong base like sodamide. You can deprotonate the proton next to the carbon which contains the halogen atom. So, this way you will be able to form a benzene. Once you form the benzene intermediate which can readily undergo addition reaction to give you an anion which can be protonated from the proton source that is present in the reaction medium. So, in this lecture we will study two more reactions which are not very common. First reaction involves the reaction of diazonium salt, which we will study in detail later. However, just we will try to see some examples. If you have the particular diazonium salt which when you heat or apply light, it can lose nitrogen molecule and you will be able to get a carbocation which can be reacted with the fluoride ion. So, you can get the fluorobenzene as the product. Then we will see some examples of halobenzenes. If we have the halobenzenes, if you have the aromatic system that contains halogen atom, you can try to do substitution reaction via radical anion intermediate, and when you react the aryl halo substrate, by it can convert into radical anion which can lose the corresponding halide ion. Once if you lose that one, you will be able to have a radical intermediate. That radical intermediate can react with the nucleophile and you can again transfer the electron. In this way the reaction can be carried out. We will see two types of reactions. Then we will see the Ullmann coupling, which is also a very important transformation in organic synthesis. If you have the aryl halide, you can try to react with nucleophile via coupling reaction. Then we will see the recent development in the aromatic system where you can try to introduce nucleophile via CH functionalization. At the end we will see the Stephens-Castro coupling reaction. Here the reaction of diazonium salt is shown, and if, for example, if you have that diazonium salt and when you apply energy it can lose nitrogen molecule. Once you form the carbocation, this carbocation can react with the nucleophile. In this way you can try to introduce nucleophile, and the mechanism operates in the reaction of diazonium salts with the nucleophile. The driving force you can see here resides in the strength of the bonding in the nitrogen molecule. So, once if you apply the energy, light or heat energy, it can lose nitrogen molecule. You will be able to generate a carbocation which can undergo reaction with the nucleophile. For example, now let us take this aniline. You can convert into diazonium salt when you react with HNO2 and tetrafluoroborate, and you can make this salt. Once you form this salt, when you provide energy, when you heat the salt, it can lose nitrogen molecule and BF3 In this way you will be able to form the fluorobenzene as a product. The reaction pathway is shown here. As you can see here, when you heat this salt, it can lose a nitrogen molecule and you will have this salt once again. This can transfer fluoride ion, so it can undergo reaction. In this way you will lose BF3. Here an example shown for this transformation. When you react this aniline derivative and with sodium nitrite, when you react with tetrafluoroborate, and you will be able to introduce fluorine in the place of NH2. First it forms the disodium salt. When you heat, under these reaction conditions, it can lose nitrogen molecule. You will have this kind of intermediate. It can transfer the fluoride ion. You can get this fluorobenzene as a product. Here another example shown. In this case, you can see here 2-aminobutadiene derivative, which when you react with sodium nitrite and this reagent, in the similar way you will be able to introduce a fluorine atom in place of NH2. And first, as we have seen, you form the disodium salt, then it can be converted into the corresponding fluoro derivative. And here also you can see here, when you react with sodium nitrite, tetrafluoroborate, you can see here it can also undergo reaction as just we have seen, and you can do the fluorination. So, if you have the aniline substrates or aromatic amines, you can make disodium salt with the HNO2 in the presence of tetrafluoroborate. You can make the corresponding salt. Once you have the salt, which when you heat, and you can get the corresponding fluoro derivative. The next reaction is the involvement of radical anion. You can see here, and this reaction can be facilitated by solvated electrons. You can also carry out the reaction in the presence of light. You can also perform this reaction electrochemically as well as by heating. The general mechanism of this transformation shown here. As you can see, when you have the halobenzene aryl halides, and when you provide the electron, and then you can form the radical ion. Once you form the radical ion, which can lose the halide ion, you will be able to have the aryl radical intermediate. Once if you have the aryl radical, it can react with the nucleophile. You can end up with a radical ion, which can transfer electron to the aryl halide. So, you can get this substituted compound where you generate again radical ion, which can further react with the nucleophile. The reaction goes on. First one is initiation. If you have the electron source, you can generate the radical ion. This propagation step, as soon as you have the nucleophile, it can undergo reaction. You will be able to generate the radical ion. This, once you have this one, this can now lose a electron. It can provide the electron to the aryl halide. In this way, you will get the neutral molecule, and you have the radical ion, which can now again react with the nucleophile. The reaction goes until you have the nucleophile in the reaction medium. So, some of the examples are shown by this synthetic route, and here the reaction of bromobenzene with this enolate shown the presence of light, in the presence of ammonia and light. So, you can the enolate can readily undergo reaction as just we have seen, and you can form the radical ion. Once you form this one, this can now undergo reaction as just we have seen, and it will be converted into Br minus, and you will be able to have this alkyl benzene. What you do here, you form a carbon-carbon bond formation. You will be able to generate this one. It involves a radical. Similarly, the another example here, and this also similar way. If you have the bromobenzene, this enolate can undergo reaction here, and you will be able to do alkylation. Mostly the enolates have been utilized for the carbon-carbon bond formation under these reaction conditions, and here you have the trialkyl bromobenzene derivative, which when you react with this enolate in the presence of light, and again it can undergo reaction as we have seen, and you will be able to get this alkyl benzene derivative. Here another example is shown. In this case, and 2-chloropyridine, the reaction of 2-chloropyridine with this enolate is shown, which can be generated from the acetone, and this when you treat this enolate with the 2-chloropyridine in the presence of light, it can undergo substitution reaction in the place of Cl2 through radical ion intermediate, and you will be able to do alkylation. And similarly here the reaction of 4-iodoanisole is shown with this phosphorus compound in the presence of light. Again this one, this can here you make a CP bond, and this case the reaction of iodobenzene with this lactone. This reaction has been carried out again in the presence of light and a strong base, and this base as we have seen you can form the radical ion. Once you form this one by electron transfer process, you have the base, it can deprotonate and it can add, then you will be able to make a carbon-carbon bond in this position. As you can see here, when you base make it and then it can undergo addition reaction, you will be able to introduce arylation at this position. The another example here again the reaction has been shown in the presence of tertiary butoxide, ammonia and light. Here also what may happen, as we have seen, you can form the radical ion. Once you form this one, now this can now react, you have the base can deprotonate this proton, then you will be able to form this one, it go here, comes here, then it can react here, then you will be able to make the carbon-carbon bond. You can make this polycyclic system. So, if you compare the two reactions that we have discussed so far, the first one involves a diazonium salt, where you can make fluorobenzene. If you have the aniline amine derivative, you can convert into corresponding diazonium salt with the tetrafluoroborate. Once if you form this one, when you heat or irradiate the presence of light, you can convert into fluorobenzene. And in the second case we have seen, if you have the halo substrate aryl halides, you can transform into radical ion, which can readily undergo reaction with the nucleophile, particularly enolates. So far whatever we have seen, most of the reactions involve enolates as a nucleophile, and you can make a carbon-carbon bond formation. In this way you will be able to construct, for example, polycyclic compound. So far whatever the example we have seen, all reactions have been carried out using light. These reactions have been performed photochemically under moderate reaction conditions. Now let us focus on the related reactions. Next one is Ullmann reaction. The reaction is shown here. If you have the aryl halide and you can try to couple, you can get the biaryl system in the presence of copper and base. If you see the original Ullmann reaction which was discovered around 1900, this reaction has been carried out using stoichiometric amount of copper. The base under vigorous reaction conditions, the reaction is usually carried out above 150 degrees Celsius, and then you can get the biaryl system. Now this reaction, the mechanism of this transformation shown here. First what happens, the copper undergoes oxidative addition, you can get this compound. Once if you have this one, so another copper can react, it can reduce the copper 2 to copper 1 by single electron transfer. At the same time now the copper 0 will be oxidized to copper 1. So what basically it is converted into copper iodide. It can give one electron, reduce this copper 2 to copper 1, and this will be oxidized to copper 1 iodide. So it will be oxidized same time, therefore you will get this as a product. This takes place via single electron transfer process. Once you form this one, now this can react with another molecule of iodobenzene, as you can see here, again oxidative addition, and this is 1. So oxidative addition, it will be converted into copper 3. Once you form this one, this can give the product by reductive elimination, and you will be able to get copper iodide. If you see the Ullmann reaction, the beginning it was carried out using stoichiometric amount of copper. Later it has been converted into catalyst system. If you carry out the reaction using ligands, this catalytic activity of the copper can be tuned. So now the last 10 to 15 years, several methods have been developed for the Ullmann coupling reaction using ligands. The reaction can be carried out now at moderate temperature below 100 degrees Celsius at milder reaction conditions using catalytic amount of copper salts. Here an example shown. In this case, the intramolecular coupling between these two aryl iodide carbon, this carbon between this and this has been shown. This can be carried out In this way, you will be able to generate this dihydrophenadiene derivative. You can see here first what will happen, as just we have seen, when you react with the copper and you can make oxidative addition, then it can react with another copper. For example, this carbon iodine bond undergoes reaction with the copper, first oxidative addition, you will get this. When you react with another copper, and it will be converted into copper iodide, and this will be converted into copper 1. This now intramolecularly undergo reaction with this carbon iodine bond via oxidative addition reaction. You will be able to you will have this intermediate copper 3, which can give the product by reductive elimination. You can get this compound, you will be able to generate copper iodide. So, now the next example involves reaction of 2-bromopyridine using copper triflate. This reaction you can see here has been shown at room temperature. If you look at the traditional Ullmann coupling reaction, which has been carried out above 150 degrees Celsius using copper, and you can see here that now you can try to carry out the reaction at moderate temperature using different copper sources and usually copper complexes when you have the ligand system. So, this catalytic activity of the copper has been shown significantly improved, and so that you can use as catalyst. This can be carried out at moderate temperature. So far we have seen the CC bond formation. Here shown the reaction of aniline with this 2-bromobenzoic acid, and this can be now coupled. You can make the CN bond amination using copper salt in the presence of base potassium carbonate. This is known as Jordan-Ullmann synthesis. This also now you can carry out amination, and you can also make ether. For example, the next one shown here, if you have the phenol, you can try to couple with this para-tetrahydrobutyl iodobenzene using copper 1 iodide in the presence of cesium carbonate, and microwave conditions you will be able to form this diphenyl ether. What you do here, you make a bond between this oxygen and this bond where you have the iodine. So, this carbon where you have the iodine. So, you can make this bond between this oxygen and the carbon. So, you can try to couple here phenol with this iodobenzene derivative using cesium carbonate, using copper iodide in the presence of cesium carbonate to give this diaryl ether. The next example involves the coupling of this amide NH with this bromobenzene. You can, in this way you will be able to make this amide derivative, which when you do the hydrolysis you will be able to get NRL amine derivative. And the next example involves here the coupling of this iodobenzene derivatives with the methoxy group is shown here. In the presence of copper 1 chloride, you can try to couple this methoxy group. In this way you will be able to make alkyl aryl ether. Here see NRL aniline derivative is shown. You can, what you do, you make a CN bond between this amide nitrogen and bromobenzene, and here this aryl iodide has been reacted with the sodium methoxide. In this way you will be able to make this alkyl ether derivative. The reaction of amide known as Goldberg reaction. The mechanism of this reaction can be understood. So, if you have, in this case you have the copper 1 iodide, let me write like this. the copper 1 iodide first undergoes reaction with this. Since you carry out the reaction in the presence of base, the phenol can react with the base. You make the phenoxide, at the same time you have the copper 1 iodide, you write here, and what you do here, you generate so you will be able to have now. So let us try to draw the mechanism for this reaction, so that you can try to draw similar way for the other substrates. First we form this again copper 1. Once you form this one, which can now undergo reaction with your aryl iodide via oxidative addition. Let me write Ar iodide. So, this is oxidative addition. So, you will be able to now once we have this one, this can give the product by reductive elimination. This is copper 3. This can give the product by in this way you will be able to complete the catalytic cycle. First, what happens here, whether amine or phenol, whether amide, which undergoes reaction with the base, you can make the anion, which can act as a nucleophile, which can undergo reaction with the copper 1 halide or copper 1 species. You will be able to form this compound. Once you form this one, which can now undergo oxidative addition with the aryl halide, you will be able to have this copper 3 intermediate. Once we have this one, this can give the product by reductive elimination, where you can try to generate the copper 1 species to complete the catalytic cycle. So far we have seen some examples for Ullmann coupling reaction. This has been well explored, in particular last 20 years. Considerable progress has been made. Now several methods have been developed. You can try to couple variety of phenols and amines, amides and aryl substrates, aryl halides to give the coupled product. In this way, you will be able to make biaryl system as well as ethers, substituted amines at moderate temperature, using catalytic amount of copper to complexes as the catalyst. Now, let us look at the recent development, the reaction of aromatic system with amines. And if you look at here, you have the benzoic acid. In its ortho position, you can see the pyrrole. This is important precursor we use for construction of variety of heterocyclic compound. So, this, if you have benzoic acid, so we can try to, if you make directly to introduce, you have the CH bond. If you replace with if you couple this pyrrole with this CH bond via deheterogeneity coupling, it will be very useful. So, the reaction condition shown here, this can be carried out if you have the benzoic acid. What you can do, you can make, try to react with the 8-aminoquinoline, you will be able to make this amide derivative. Once you form this one, so now you can try to react with azole or pyrrole and analogues and the presence of copper 2 acetate and cesium carbonate. This acts as a base under these conditions. When you carry out the reaction using this reagent shown a 1.5 equivalent of copper 2 acetate and 2 equivalent of cesium carbonate, you can try to introduce azole via CH functionalization. And here shown not only pyrrole, you can also introduce indole and carbazole and this pyrazole, they work very well. And you can have variety of other substituent, like for example, you can have here Cl chloroiodo substituent methoxy methyl nitro group. The reaction works efficiently. If you look at here, the reaction always takes place the ortho CH bond, which is less reactive comparing to this carbon halogen bond. However, here the activation of the CH bond takes place, then this azole coupling occurs, and this is some of the example. Now, let me show you the reaction pathway, how it takes place. After the reaction, what you can do, you can also do base hydrolysis, and you will be able to get the 2-pyrrole benzoic acid. Just we have seen, we use precursor to make variety of heterocyclic compound. So, what basically so far whatever you have seen the reaction, the case of aromatic nucleophilic substitution reaction, always you should have a activated aromatic system. For example, if the beginning we have seen, if you have a strong electron withdrawing group, and if we have leaving group, the reaction can take place at the carbon of wherever you have the leaving group at para or ortho position with respect to the electron withdrawing group, and the reaction takes place addition elimination. We have seen the last class. Then we have seen some of the reaction through benzene mechanism. Today's class we have seen if you have aniline derivative that you can convert into diazonium salt, and if you make diazonium salt of tetrafluoroborate, then you can try to convert into the corresponding fluoro derivatives. Then we have seen the reaction that involves a radical ion intermediate. If you have the halo substrate, you can convert into alkyl benzene via what you do here, you form a radical ion by several approaches. We have seen the use of light. Once you form the radical ion, which can readily react with the nucleophile. Then we have seen the Ullmann coupling reactions. If you see all these substrates, they are functionalized aromatic system. Here functionalization you do here CH bond. This is quite efficient route because automechanomical you can have broad substrate scope. So, if you for example, if you have the benzoic acid, you can make this auxiliary, you can try to react with the 8-aminoquinoline, you make the amide. You can use the amide to chelate with your metal salt, then activate the CH bond. In this way, you will be able to introduce the azole moiety. The reaction pathway is shown here. Since you have to carry out the reaction at the presence of base, you can deprotonate. So, when you have this pyrrole, when you react with the copper to acetate, one molecule of acetic acid goes out, then you will be able to have this copper 2 intermediate. Once if you have this one, now again you have the base, it can deprotonate and another molecule of acetic acid can come out, and you will be able to have the acetic acid in the presence of base will be converted into cesium acetate. You have the copper 2 intermediate. Once if you have this one, this can be oxidized to copper 3 using copper 2 acetate, which will be converted into copper 1 acetate through electron transfer. Now, you will have this copper 3 intermediate. Once if we have this one, now it can activate the CH bond intramolecularly, and you will be able to have this copper 3 intermediate. Once form this one, this can give the product by reductive elimination. In this way, you can make a carbon nitrogen bond at the ortho position with respect to the amide substituent. At the ortho CH bond can be activated, you can make a CN bond. So, now let us look at one more example. Just we have seen if you have the acid, for example, benzoic acid, I can convert into amide. So, you can react with lose. So, you can try to make amide. So, we have seen, if you have this one, you can make the amide, you can activate this CH bond, you can introduce the azole group. And here, if you have aniline, you can also try to do similar way. For example, take the naphthylamine. Once if you have this one, similar way, you can try to react with this carboxylic acid you can make So, this once you form this one, now this can make chelation with your metal, activate this CH bond. In this way you can try to also introduce the acyl group. You can make the CN bond formation. For example, here the reaction of indole is shown. You can activate the CH bond, you can introduce the indole group. This is also very useful reaction. As you can see here, variety of indole derivatives can be coupled, and so you can make a carbon nitrogen bond. The reaction pathway of this transformation shown here, as just we have seen in the presence of base and copper to acetate and this one. So, you will be able to form this intermediate. Once you form this one, so you can lose one molecule of cesium acetate and then you can form this intermediate. Once you form this one, now this can further react with the indole. So, the base you can have this intermediate, this is copper 2. Once you form this one, this can, as just we have seen, it can be oxidized to copper 3, and where using copper to acetate, which will be reduced to copper 1. So, this can give the product by reductive elimination. Once if you have this one and this in the presence of base, and what you can activate the CH bond, the comma CH bond, then you will be able to have this copper 3 intermediate. Once if you have this one, this can be converted into the product by reductive elimination, where you will generate the copper 1 species, and since you have the acetic acid and oxidizing agent, it will be further oxidized to copper to acetate to complete the catalytic cycle. Just we have seen two examples, and where you can also introduce azoles. You can make a CN bond formation. You can convert CH bond into CN bond formation via CH functionalization. By what you do here, you have a directing chelating group in your substrate, so that which can chelate with your metal catalyst, activate the CH bond through cyclometallation. You form a carbon metal bond. Once you make the carbon metal bond, then you can try to introduce the functional group, in this case azole, and you can make a carbon nitrogen bond. So, in this way you will be able to make variety of functionalized aromatic systems. Now, let us look at one more example in this topic, and you can see here, and just we have seen the activation of this comma CH bond through using copper to acetate, and when you can try to couple with azole. We have seen some examples for the reaction with the indole. So, here the reaction with the boronic acid is shown using copper to acetate, and here you can make this ether. This is also very important compound. You can convert the CH bond into aryl ether, and this also you can see it is this unit is present in several medicinal important compound, and this is also very important transformation. The mechanism of this transformation shown here, and if you see the paper, you can find this reaction also quite gentle. Variety of substrate can be reacted with the boronic acid to make the corresponding ethers. As just we have seen, the presence of base and copper to acetate can react with your substrate. You will be able to form this copper to intermediate. Once you form this one, this can be oxidized to copper 3 by copper to acetate, which will be converted into copper 1. When you have the copper 3, now it can activate this CH bond. You can see here you have the copper 3 intermediate. Now, the boronic acid can, as shown here, can react with the base and water. You will be able to form this intermediate. This will be converted in the presence of water into phenol. The reaction medium, once you form this one, now since you have the base, you can make the phenoxide, which can, now the phenol can react with this one, and you will be able to form this intermediate. This also copper 3. Once you form this one, This can give the product by reductive elimination. You make a bond between this carbon and this oxygen, and you will be able to make the ether derivative. So, this reaction is usually carried out in the presence of using phenol, and here the boronic acid has been used. The boronic acid is converted into phenol in the reaction medium. Once you form this phenol in the reaction medium, it can readily react with this intermediate, and you can form this copper 3 complex. Once you form this one, this can give the product by reductive elimination. So far we have seen some examples how you can try to introduce nucleophile in the aromatic system. We have seen the two examples for CN bond formation and one example for CO bond formation using transmetal catalyst, in particular copper based system. This reaction has been well explored the last couple of years. For your understanding, I have shown 3 examples. Now you can try to introduce variety of nucleophile the aromatic system via CH functionalization. If you have a functional group, if you have the catalyst systems, you can try to activate the CH bond. You can make the carbon metal bond, then you can try to introduce the nucleophile. The next one is Stephens-Hastrow coupling reaction. This reaction we have seen earlier, and let me show once again briefly. And if you have the aryl halide, for example here iodobenzene, this can be readily reacted with the terminal alkyne in the presence of copper 1 halide. If you have this terminal alkyne, the presence of base, the mechanism shown here. If you have the copper 1 halide and if you have the terminal alkyne, you can try to, in the presence of base, you can make this copper 1 alkyne species. Once you form this one, this species can now react with aryl iodide, in this case here aryl iodide by oxidative addition, you will form this copper 3 intermediate, and this copper 3 species can give the product, coupled product via reductive elimination. You generate the copper 1 species. What you do here, you make a carbon carbon bond between this carbon of the iodobenzene with this carbon of this terminal alkyne. You can make a carbon carbon bond. In this way you can try to make aryl alkyne derivatives. So, in this way you can make variety of alkynyl derivatives, which also widely used in organic synthesis for the functional transformations. Here some examples are shown for this Stephens-Hastrow coupling reaction. The first reaction you can see here, the reaction of this alkyne, the presence of base, as just we have seen, you can make the corresponding copper alkynyl derivative. Once you form this one, as just we have seen, now this can undergo oxidative addition here, and then you will be able to have so this can be converted into by reductive elimination. Once you form this one, this can also cyclize. Since you have the copper system, it can undergo intramolecular cyclization. So, in this way you will be able to form this lactone. So, when you have this 2-iodobenzoic acid and this copper alkynyl derivative, once if you have this two, when you heat and DMF, when you reflux a DMF solvent for a longer time, it can undergo CC coupling followed by intramolecular cyclization to give the lactone. And in this reaction, as just we have seen, and you have the base copper 1 iodide triphenyl phosphine. Once this under these conditions, as just we have seen, you can make the corresponding copper alkynyl intermediate. Once you have this one, which can undergo oxidative addition with this vinyl iodide derivative. Once you form this copper 3 intermediate, which can give the product by reductive elimination. In this way you will be able to form this macrocyclic lactone as the product. So, Stephens-Hastrow coupling finds broad utility in synthetic chemistry, and if you have the terminal alkyne, you can make react with the copper 1 halide, you can make the copper alkyne derivative. Once you have this one, this can be readily coupled with aryl halides or vinyl halides. First one involves the coupling of iodobenzene derivative, next one involves the coupling of vinyl iodide. You can make CC bond formation. In this way, you will be able to make macrocyclic systems. In summary, so in this class we have seen 5 types of reactions. First one, we have seen the reactions of diazonium salt. If we have the aniline derivatives which can be readily reacted with the tetrafluorophorate and sodium nucleophilic substitution reaction. If you look at there, if you have the electron source, it can be converted into radical ion. Once if you have the radical ion which can be readily reacted with the nucleophile, and this radical reaction, and until you have the nucleophile, the reaction can be facilitated. This reaction has been widely used to make a carbon-carbon bond formation, particularly if you have the enolate, it can be readily reacted with aryl halide to make the corresponding alkyl derivatives. Then we have seen the Ullmann coupling. If you have the aryl halide, you can try to couple them via CC coupling using stoichiometric unit of copper under heating conditions. This reaction has been also now improved. You can also carry out the reaction using catalytic amount of copper 1 sources using ligands. We have seen some examples also for the CO coupling and CN coupling. If not only you can couple the 2 aryl iodides to give the biaryl systems, if you have aryl halides, you can also try to react with the phenols and anilines and amides. You can make CO and CN bonds. We also have seen the mechanism. First, what happens, this the phenol or aniline or amide undergoes reaction with the base. You generate the corresponding anion which can undergo reaction with copper 1 iodide. By a substitution reaction, you can get the copper 1 intermediate. This copper 1 intermediate undergoes oxidative addition with the aryl halide. You will generate the copper 3 intermediate which can give the product by reductive elimination. In this way, you will be able to form diaryl ethers, aryl amines in good yields. This reaction has been now well explored, and you can carry out the reactions at moderate temperature in good yields with broad substrate scope. Then we have seen the recent developments, the CH functionalization for the introduction of azoles in the aromatic system. For example, if you have the benzoic acid or aniline derivatives, you can try to couple selectively CH bond regioselectively using the diaretic group. You can introduce azoles. We have some examples. Similar way, you can also try to react with the phenols, other nucleophiles, aliphatic amines. This reaction also has been well explored, and copper, palladium based catalyst systems are considerably explored. Then we have seen the Stevens-Castro coupling reaction. This reaction also has been already discussed in another lecture. However, you can once again we can try to briefly understand this reaction. If you have that alkyne which can be readily reacted with copper 1 halide in the presence of base, you can get the corresponding copper 1 alkynyl derivative. Once if you have this one, this can be readily reacted with aryl halide. For example, if you have the iodobenzene, you can make CC coupling. Then we have seen 2 examples. Depends upon the nature of the substrate, you can also try to make macrocyclic systems. We have seen one example, and you can where you can try to couple terminal alkyne with vinyl iodide using this Stevens-Castro coupling via CC bond formation. This provides efficient synthetic route to construct this kind of scaffold, otherwise it is very difficult to make this molecule. With this we conclude this lecture. Thank you very much.